Tamia. So let me get her here. Okay. Oh. All right. And it's going to take me just a couple of minutes to get. Oh, wait, I think I've got it here. Let me try it here. Okay. And this is, I'll pull up the PDF version, I think. Now this is the 2-page test, right? Okay. All right, let me move this up here. Okay, does that look like the test? Wait, you can't see it. Let's do a new share here. And there we have it. Okay, does that look like the test you're talking about? Okay, which question? Oh, right at the very end, near the end. Okay.
When it says f of x slash a plus 1, are you saying x over x plus 1 or x over 8 plus 1?
Okay. Oh, okay, got it. I see what you. Okay, I understand now what you're saying. Okay, this is 1/8 of x plus 1. Okay, the x over 8 is the first term, plus 1 is the second term. Is that okay? Is that what you were meaning? Yeah, that's it. Yeah, this is the first term is 1/8 of x, and then plus 1. Okay, good question. Those are always hard to type and hard to interpret, so I'm glad you asked that. Okay, any other questions before we get going on today's? Okay. Okay, I mean, no problem with it now. You may forget it. I may forget to ask. Any things you want to wait till the end? Okay, just don't forget, because I'll forget. I mean, it'll fly the coop. Okay, so what I'm going to do is, I think I'll close this test unless there's any other questions about the test. It'll be out there if I need it. And let's go back to 2.2, and it seems like everything I set up before is this taskbar moved back in the way. So let me move that back again. Okay, it said screen sharing has stopped, but it looks like it's still screen sharing, right? You can see polynomial and rational functions. And we'll go from current slide. What I can't see is my recording anymore. Let me make sure it's still recording. Oops, D is here. Let me get D marked here. All right. That should have us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's make sure we got 12 students here. Yep, 12 students. Nobody else waiting. Okay. All right. We'll go from current slide. Well, I was trying to check and make sure Screencast-O-Matic was recording. I had it recording. Yes. Okay. Why it's not showing up in the bottom left, I don't know, but it's not. Okay, we'll go from current slide. Oh, there it is. It's showing up now. Okay, any other questions, issues, concerns, problems? Okay, I guess you know what day it is today. Janae's got the V there for voting. Okay, I hope you've already voted, but if you haven't, please make time today. If you're registered and can vote, please vote. It's very, 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 very important, and hang with that. Okay. So any other questions, concerns, problems? All right, we're still in Chapter 2, Polynomial and Rational Functions. The first 5 sections will be dealing with polynomial functions, the last section with rational function. And here comes Quenisha. So let me get her marked here. Okay. Okay. Let me make sure nobody else is waiting. It should be 13 students, lucky 13. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Got it. Okay. So we're dealing Chapter 2, Polynomial and Rational Functions. I can't get the screen to advance. There we go. We're starting today Section 2.2, Polynomial Functions of Higher Degree. Now what do we mean higher degree? Well, in 2.1 we dealt with quadratic functions. Okay? Quadratic functions, which are degree 2. Now we're going to deal with polynomial functions of higher degree, 3 or more. Okay? So we'll use transformations to sketch graphs of polynomial functions. Hey, do you think that comes as a surprise that this author loves to sketch graphs? Okay? We'll use the leading coefficient test. I like to call it the leading term test. I think it says a lot more, and it's not just the leading coefficient, it's the leading term test to determine the end behavior, what's happening in the long run once we get Tommy here. Okay, hold on just a minute and let me get Tommy marked here. Okay, so that gets us up to 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Should have 14 students. Let's see what we got. No, we got 13, so we must have lost somebody. Okay, hopefully they will be back. Okay. All right. Now, like I said, we're just starting section 2.2. The objectives are use transformations to sketch graphs of polynomial functions. Use the leading term test, I call it, to determine the end behavior of the graphs. What happens in the long run? Okay, and then we'll find and use real zeros of polynomial functions as sketching aids. Guess what? Graphing again. Okay, and now it won't advance. And then finally we'll use the intermediate value theorem to help locate real zeros of polynomial functions. Okay, in the next section we'll do more about finding those zeros. So let's start with graphs of polynomial functions. Now I apologize ahead of time. This past weekend we got a lot of work done over at the farm in Georgia. We were burning a lot of sticks and things that have happened, but in burning that and then also doing a lot of mowing and stuff, I really got exposed to the elements and came away with a sore throat. So hopefully I'll be able to make it. It's better today than it was yesterday, but I haven't taught 4 classes yet today, so we'll see how it goes by the end of the day. But I apologize if I do sound sort of hoarse. My wife said I was sounding hoarse, and here's D. That's who we lost, and he's coming back. So I already marked him present. Okay, and that should have us back up to 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Should have us back to 14 students. Yes. Okay. All right. Now, we're in Chapter 2, Polynomial and Rational Functions, still on polynomial part. Section 2.2, Polynomial Functions of Higher Degree, because 2.1 we dealt with second degree, polynomials, which are quadratic polynomials. Now we're going to be talking about graphs of polynomial functions of higher degree, and just generally this. In this section, we'll study basic features of the graphs of polynomial functions in general. The first important feature of polynomial functions, they're always continuous. You never have any breaks or discontinuities in them. They're always continuous. This is an example of a function that could easily be a polynomial function. Okay? Now I mentioned continuous here. To me, like peanut butter and jelly, okay, I always say smooth and continuous. Okay, we're going to talk about the smoothness later, but this is a continuous part now. Essentially, that means that the graph of a polynomial function has no breaks, no holes, no gaps. Everything is continuous. No discontinuities at all. Now, that could be, probably is a polynomial function, the graph of a polynomial function. Now, here's what a polynomial function, well, doesn't look like, okay? This graph is an example of a piecewise defined function that is not continuous. Now this piece over here may be a polynomial piece. This piece up here may be a polynomial piece, but they're not the same polynomial functions. There is a gap there, okay? That is not continuous. This is not a polynomial function per se, okay? Each piece may be polynomial, but the total function is not a polynomial. Okay? So, polynomial functions are continuous. That one is not. The second feature of that a graph of a polynomial function has only smooth, rounded turns. Okay? I think of it like jazz, really smooth. Okay? Here, even though that's fairly steep turn here, it's still smooth. No points. Okay? No jaggedness, okay? Nice smooth curves here. So polynomial functions are not only continuous, they're also smooth. Rounded turns, the graphs are rounded turns. They have smooth rounded turns. I've said it about 3 different ways now. Okay, here's an example of one that's not a polynomial function. This has a corner in it, not a smooth transition. It's continuous for sure. Absolute value function, it's a continuous function, but it's not smooth down here. It's pointed, okay? It makes a sharp turn to the left, okay, when it hits the origin. A polynomial function, even though it's pretty sharp there, it's always smooth, okay? Always smooth, okay? This one, not smooth. Very quick bend. Now this is sometimes called a corner or a sharp turn at the point. Others sometimes are called cusps, okay? Even sharper than a corner is, and certainly they can't be discontinuous. Now, goodness, my throat's hurting already. The graphs of polynomial functions of degree greater than 2 are more difficult to analyze than the polynomials of degree 0, which is a constant function, degree 1, which is a linear function, or degree 2, which is a quadratic function. Those are really easy to do. These polynomial functions of higher degree, a little bit more involved. Okay, so let's talk about some of those differences. However, using the features presented in this section, coupled with your knowledge of point plotting, intercepts, symmetry, those kinds of things, you should be able to make reasonably accurate sketches by hand, okay? If you have graphing utilities, you can make even nicer ones, okay? The polynomial functions that have the simplest graphs are the monomials of the form f of x is equal to x to the nth power, where n is any integer greater than 0. Because if it's x to the 0th, that's a constant function, okay? X equal or n equal 1, that's a linear function. We've already dealt with those. N equal 2, that's a quadratic function. We've already dealt with those. So basically, going to be focusing on those quadratic functions where n is actually greater than 2. We'll mention 2 and 1 and maybe 0 again, but we're going to focus on those greater than 2. All right, now here is the beginning of this, and by the way, this is over on page 124 now. From this graph, this figure, 2.9, you can see when n is even, that power of the variable is even, the graph is similar to your quadratic function. Here is that light blue graph is the quadratic function, y is equal to x squared, okay? When you go up to x to the fourth, it looks very similar. 3 points are always the same, okay? Negative 1, 1, 0, 0, and 1, 1. Those 3 points are the same whether the graph is x squared, x to the fourth, x to the sixth, x to the eighth. They all look very similar. Here's the difference. When the higher the power, the sharper it comes down through minus 1, 1 and goes up through plus 1, 1. Okay? The steeper it gets, the higher the power. The flatter it gets near 0, 0. And here's Terrell. Okay? Let me mark Terrell here. Okay, that should get us up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 13, 14, 15. Should have 15 students now. Let's see what we got. Yeah, 15 students. Nobody else waiting. Okay. Okay. Terrell, if you're in now, we're in Chapter 2, Polynomial Rational Functions, Section 2.2, Polynomial Functions of Higher Degree. We're talking about those higher than 2, okay, because we dealt with quadratic functions in Section 2.1. And we're on page 124, top of the page. Okay. When n is even, the graph of any of your polynomial power functions, f of x is equal to x to the n, when n is even, they look a lot like your parabola. Okay? Here's the difference. They are steeper when they pass through minus 1, 1 and pass through 1, 1. They're steeper there. Okay? And near 0, 0, they're flatter. Okay? So that's the difference. X to the 6th would even be steeper than x to the 4th. Flatter down here, steeper here. And it just keeps getting steeper and steeper on the outside and flatter on the inside. Now, when n is odd, okay, this is the cubic function, f of x equal x cubed. That's the light blue curve here. And though they're all nice smooth curves, but again, 3 points are in common, minus 1, 1, minus 1, minus 1, 0, 0, and plus 1, plus 1. Okay? X to the 5th would be steeper at the minus 1, minus 1, and plus 1, plus 1, but flatter near 0, 0. Okay? So, same type deal, except even functions are on the up and up, odd functions go in opposite directions, odd powers, okay? And these are odd functions as well. Any questions on those? And all the ones past those, the what I call the power functions, x to the 4th, x to the 6th, x to the 8th, x to the 10th, they just get steeper and steeper here, flatter and flatter here. X to the 5th, x to the 7th, x to the 9th, x to the 11th, steeper and steeper here and here, and flatter near 0. Okay? Those are your basic graphs of your power functions, those special kinds of polynomial functions. Okay. And I can't get my screen to advance, so here we go. Moreover, the greater the value of n, the flatter it is near the origin, the steeper it is at plus and minus 1. Here's example 1. It says, sketch the graph of each function and we'll go from there. Okay, now extraneous mark there. Let me see if I can clean that. Okay, now let's see if I can draw a reasonably vertical line and a reasonably horizontal line. Okay, we'll tick off a few points here. 1, 2, 3, 4, 5, 6, 7, 8. Negative 1, 2, 3, 4, 5, 6, 7. Positive 1, 2, 3, 5, 6. You can't see them up there. 7, 8 maybe, something like that. Negative 1, 2, 3, 4, 5, and on down. Okay, so let's sketch the graph of each of these functions. F of x equal minus x to the fifth. Well, we know 3 points right off the top, right? When x is equal to 0, y is equal to 0, right there. F of x is equal to y. So but when x is equal to 1, 1 to the fifth is 1, but then negate that and you have a minus 1. So it's down here. Okay? When x is equal to minus 1, minus 1 to the fifth is positive, no, is minus 1, but then when you negate it, it becomes a positive 1. So there's the next one. Okay? And then the next one after that, x equal 2. 2 to the fifth is 32, but negative. So it's off scale immediately. So here's what the graph looks like. Kinda. I can't draw these very well. Comes down really steep there, flattens out quite a bit here, and then goes really steep here because it's heading to, before it gets to x equal 2, it's going down to y is equal to minus 32. So that's the first graph. Okay? What that is a reflection across the x-axis of your x to the fifth function. So let's just flip back a slide or two. There was your x to the fifth function, this black line here, and they flipped it and made it come down like this. Okay, so that is your first function. Probably I need to be a little flatter in there, but I'm not very good at drawing these things. Now, let's go to, let's change my pen color. Do y'all have a preference on pen color? We got black, orange, yellow, green, light green, dark green, light blue, middle blue, dark blue, and lavender or purple. Dark blue. Okay, let's go with dark blue here. Right there. Okay, so we'll do h of x in dark blue here. Okay, what do we notice here? The x is moved. Now remember, anything dealing with x goes in the opposite direction, so it's a plus 1, so it moves to the left. So there's going to be our origin right there, okay, so to speak, okay, right there, okay, because when x equal minus 1, your y is 0. Minus 1 plus 1 is 0, raised to the fourth, 0, so the h is 0 right there, okay. If I could just get that to, okay, there, we colored in better. Okay, now, this is an even function, so from here, it goes up to, when x is 0, this is 0 plus 1 is 1, raised to the fourth power is 1. When x is minus 2, minus 2 plus 1 is minus 1, raised to the fourth power is plus 1 again, okay? When x is equal to 1, 1 plus 1 is 2, 2 raised to the fourth power is 16. So those go off scale really, really fast, okay? And then they come down and flatten out near 0 really, really flat. Not our 0, our turning point there, vertex, and then they go up really, really sharp. Now this is probably not as flat as it should be, but that's generally what the second one looks like. Horizontal shift to the left one, and then it's a lot like this function here. See, I'm not quite as flat as they are, and so it goes up here, but shifted one to the left because of that horizontal shift. And here comes Janae. She was already here. Let me see if I can get her back in. My pen won't move. There it goes. So Janae's here. Let me make sure I do have her marked. Yes, I do. Okay. So hopefully, there she popped back in. Still 15 students. I think that's right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Got it. Okay. Any questions then? It won't advance. This is so irritating. Okay. There's what those two functions look like. Let me erase my scratch here so you can see how they are going to plot them. Okay. The first is an odd degree. The degree is 5. So the graph is similar to the graph of y is equal x cubed, but the minus sign reflects it across the x-axis. The higher power makes it steeper through -1 and +1, flatter near 0. So there's what theirs looks like. They really expanded the x and the y scales, so they emphasize that flatness. Okay, and here is Ashford. Let me get Ashford here. This is his first appearance today, so let me get Ashford. Top of the alphabet is doing pretty strongly. Bottom is going fairly strongly. The middle part's a few more gaps. So should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Should have 16 students here. Yep, that's right. All right. Now, Ashford, your microphone was on. If you have something to say, perfectly fine, but otherwise it's picking up a lot of background. Okay, got it. Thank you. Okay. We're on in Chapter 2, Polynomial and Rational Functions, Section 2.2, Polynomial Functions of Higher Degree than 2. And that's what we've been dealing with. We've just done Example 1, which is on page 124. I've failed to mention it's also located at larsonprecalculus.com. You can see an interactive version of this type of an example. Okay, and we're doing, I've just shown their f of x is equal to minus x to the 5th. Notice it's reverse of what it normally is because of the minus sign that's reflected across the x-axis, but steeper through -1 and +1, flatter near 0. Okay, the B one here, this one, is now the graph of x plus 1 to the 4th. Here we have a horizontal shift 1 unit to the left. Remember, everything dealing with the x's are backwards. It's a +1 here, so we moved it to the left one there. So your vertex is down here, flatter near the vertex and steeper on either side of the vertex. It's a left shift by 1 unit of the original graph, if you wanted to call it that, y is equal to x to the 4th. Excuse me. I've got a sore throat, so I have to stop and soothe it a little bit every now and then. So there's example 1. Any questions on example 1? Okay. Now, there is a checkpoint. By the way, every example usually has a checkpoint, so please do the checkpoints as soon as you can out of the class. Now, the book calls this the leading coefficient test. That next thing we're going to talk about. I prefer to call that the leading term test. Sure, the leading coefficient is important, but the entire leading term is important. So I'll explain why I say that. Okay. In example 1, go back to example 1, both of those Okay, remember how they look there. Note that both graphs eventually rise or fall without bound as x moves to the right or left or right. Okay, let's show this again. Well, they're not going to show them on one graph. So if it's an odd function, this one happens to be going up and never turns around again. Keeps going up, up, up. And over here, it keeps going down, 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 down. Okay? That's a characteristic of polynomial function. The farther you are from basically your origin, the center of that graph, the further you are, then it's either going up or down without bound. Okay? This one going up and up without bound. That's never going to turn around again. It just keeps climbing, keeps climbing. Okay? So, I can't get it to advance. Okay? And that's what they're noting here. In example 1, notice that both graphs eventually rise or fall without bound as x moves to the left or to the right. Okay? Now, what are we talking about then? What we're talking about then is basically the end behavior. What happens when x gets very, very large negatively or very, very large positively? That's what we're talking about. And polynomials are eventually going to go really high up or really high down. Always. Okay? When x moves to the left or to the right, far distances from the origin. Okay? Whether the graph of the polynomial function eventually rises or falls can be determined by the function's degree, that's even or odd, and by the leading coefficient, positive or negative, as indicated in the leading coefficient test. Why do they call it that? If they just said leading term test, that takes into account the degree and the coefficient. So why they call it leading coefficient test, I don't know. Yeah, that's important, but the leading term test, that covers even more ground. So here's what we mean by that leading term test. As x moves without bound either to the left, very negative, or to the right, very positive, the graph of a polynomial function, and this is what the generic polynomial function looks like. F of x is equal to some coefficient, a sub n. This n here means basically nothing except it's the coefficient that goes with the nth power. That n is important. That's x raised to the nth power. This subscript n indicates it's the coefficient that goes with that nth power. So a sub n x to the nth plus a sub n minus 1 times x to the n minus 1 plus a sub n minus 2 times x to the n minus 2. Keep on counting down till you get a sub 3 times x cubed plus a sub 2 times x squared plus a sub 1 times x to the first plus a sub 0 times no power at all for your x. It's 0 power there. Now, that's your polynomial function, okay, the generic form of a polynomial function. It's either going to be going up or down in the long run, when x is very negative or x is very positive. So let's start when that n, the maximum exponent, is odd. Now, we saw this before a couple of different ways. There, x is odd, x to the fifth, okay? It's going up to the left, down to the right, okay? Here, when x is odd, cubed, going down to the left, up to the right. X to the fifth, down to the left, up to the right. Okay? We'll come back and pick up the evens in a minute. Okay? But when n is odd, either the function is heading south to the left, north to the right, it's going one of those directions. Okay? If the n is odd, that means it's going in an opposite direction, one to the left, one to the right. Here's how we express this. As x is going very, very, very large negative, f of x is also going very, very, very large negative. If x is going very, very large positive, f of x is also going very, very large positive. When is this true? Anytime the leading coefficient is positive. Okay, now think about this for a moment. If x is a large negative number, but n is an odd exponent, then x to the nth is going to be very, very negative. Now, if that a sub n, happens to be positive, then positive times negative is negative. So it's going downhill very rapidly. But if x is very positive, x to the nth is very positive, and if that coefficient is positive, it's going very, very high to the right. Okay, so it's going toward negative infinity as x goes to negative infinity, positive infinity as x goes to positive infinity. That's if the leading coefficient is positive. It doesn't change the value of the function. Okay, now if that leading coefficient is negative, though, again, a negative number here for x raised to an odd power is always going to be going very negative, but if you multiply it by a negative coefficient, that flips it and makes it go positive. So this is going to the up, and this one's going down, because your negative coefficient, if x is very, very large positively, doesn't matter what the value of n is, that's going to be incredibly large number. Okay, but if that a is negative, then that makes it an incredibly negative number. Okay, so you see, flipping that leading coefficient, okay, will reverse the direction. Normally an odd function is down to the left, up to the right. Okay, but if your leading coefficient is negative, it reverses it. It's up to the left and down to the right. Okay, now that's what to remember about when n is odd. Now, what happens to all these terms in the middle? We're only focusing on the leading term, what the power of that term is and what the sign of the coefficient is. That's all we focus on. What other things are happening here, that determines what happens in the middle here and in the middle there. All kinds of gyrations could be going on. To be a polynomial, it has to be smooth and continuous. We know that. But all sorts of things. What this is telling us is only what's going on in the long run. Very large negative, very large positive. Okay. Now, when n is even, though, it doesn't matter what, whether n, the x is positive or negative, because if you raise a negative number to a very large even power, it's always positive. Raise a positive number to a very large even power, it's always positive. So as long as that leading coefficient is positive, this is going to be on the up and up. Okay, always. But if that leading coefficient is negative, it's going down and it's going down. Okay, so odd exponents go in opposite directions. Okay, and for very large positive numbers, if that a is positive, then that's going up. Very large negative number, that's going down. That's if n is odd. If n is even, it's going the same direction, either up and up or down and down, depends on that leading coefficient. If that leading coefficient is positive, it's got to be going up and up. If its leading coefficient is negative, it's got to be going down and down. And here's how we express it. As x goes to negative infinity, f of x goes to infinity. As x goes to positive infinity, f of x goes to positive infinity. That's when n is even and the leading coefficient is positive. However, if n is even, the leading coefficient is negative, everything is going down in the long run. Now, what happens in between here? That's what happens, determined by those terms that are in the middle. The end behavior is determined by that leading term alone. Okay, does that make sense? Now, you'll see this on tests or quizzes or whatever, And when you're talking about end behavior, your response is going to look like this. Notice what's happening for polynomial functions. I usually start with the x. As x goes to blank, f of x goes to blank. As x goes to another blank, f of x goes to another blank. Same thing on every one of these, okay? Now notice what is in every blank. In every blank is there an infinity. You're going x going to negative infinity, x going to positive infinity, x going to negative infinity, x going to positive infinity, x going to negative infinity, x going to positive infinity, x going to negative infinity. Okay, those blanks, you know what the answers are already. Every blank has an infinity in it. Every blank. Now, the x's, one's positive, one's negative. Always. Always, okay? So you got those two signs are already fixed. So all that you're determining when you're doing this end behavior is what is the sign of your f of x, okay? If the n is odd, the f's are opposite signs. If the n is even, the f's are the same sign. So then to that point, just figuring out whether they're positive or negative. If that leading coefficient is positive, then a positive x here will produce a positive f of x. A negative x here will produce a negative f if n is odd. If that leading coefficient is negative, then a negative x will produce a positive f of x. A positive x will produce a negative f of x. That's what you're determining. If the n is even, that leading coefficient is positive, everything is positive because x to an even power is always positive, and if that leading coefficient is positive, then everything's still on the up and up. However, if that leading coefficient is negative and n is even, everything's going south. Negative f of x in both cases. Okay, so basically when you fill in the blanks here, be sure you put an infinity in every blank. Be sure one of the x's is positive and one is negative every time. So you got the x's done. One's positive infinity, one's negative infinity. Any one of these, that's what it's going to be. Your f's are also going to be infinities. Then all you have to do is figure out what sign of those infinities. So it's really almost a gimme, okay? You should get most of those blanks correct. Those signs are the only thing that will trip you up. So let's do it here. Let's apply the leading term test. Describe the right hand positive and left hand negative behavior of each function. Okay? You tell me, what do you think this first one's going to do? Now I'm going to write it out just like I'll write it out on the fill in the blanks on the test. Okay? Okay, we're still in purple. No, dark blue. You want to go back to black or red, or does it matter? Stay in dark blue? Someone let me know. Well, I'll leave it there. As x goes to blank, f of x goes to blank. As x goes to blank, f of x goes to blank. That's what we're going to do on every one of these. Okay? Guess what goes in the blanks? Infinities. Every one of these is going to be an infinity. You should get that right. Right? There's your infinities. The x's, one of them is going to be negative and one's going to be positive. It doesn't matter which one you put where, I don't care. But it's always one negative, one positive. Now, what we have to determine is what in the world is happening to the f of x when x is very large negative. Well, just pick a large number, and they don't have to be that large either. Like 10. 10 cubed is 1,000. Okay? but 10 to the minus 10, this is a minus 10. Minus 10 cubed is negative 1,000. But when you negate that, that makes that go positive. Okay? When x is positive 10, x cubed would be 1,000. You negate that, and that goes to minus. And I can't get my, okay, there's a minus sign. Okay, so at x is negative infinity, f goes to positive infinity. As x goes to positive infinity, f goes to negative infinity. They're all going to be large numbers, infinities. Okay, all you have to do is determine the sign. Normally, if that wasn't a minus sign there, when x was negative, this is going to be negative. However, with the minus sign there, it makes that positive. Similarly, for very large x, if x was positive, without the minus sign there, that would be a very large positive number. With a minus sign, it becomes a very large negative number. Okay, does that make sense? Let me see if I can write them a little smaller this time. As x goes to blank, f of x goes to blank. As x goes to blank, f of x goes to blank. And guess what? Every one of the blanks is going to be an infinity. Go on and write them in. You know they're going to be infinities. Okay? They've got to be. For polynomial functions, they're going to be infinities. One of these x's is going to go to negative. The other goes to positive. You got those done. Okay? Now the question is, what does the function do? Well, guess what? That's an even power, positive coefficient. No matter what x is, positive or negative, when you raise it to an even power, that goes to positive. When you don't negate that, it stays positive. So this f is positive, that f is positive. Done. You are finished. You got them done. Okay? Any questions on that? Okay, this one would be as x, for some reason the pen is not writing, and I don't know why. I don't know why this device does weird things like this. I can't even find the pen now. Okay. I do not know why the pen is not writing. I'm just drawing all over the screen and the pen is not anywhere in sight. Okay, there it is. There's the cursor. I can see it now, or I could see it. Okay. Let me do this. Let me see if I can. Oh, there it goes. Okay, let's see if that helped. As x doesn't seem to be cooperating at all. Okay, I can't write on the screen anymore, folks. Sorry about that. Let's talk through it. Okay, as x goes to blank, f of x goes to blank. As x goes to blank, f of x goes to blank. Okay, my pen is not responding at all to anything. Okay, now one of these x's, all the blanks have infinities in them, all four of the blanks. The first x, it doesn't matter which you do. I like to do negative infinity. It doesn't matter. And the second x is positive infinity. Those have to be different. Okay. Now, as x goes to negative infinity, which we have right here, as that x goes to negative infinity, then a negative number raised to an odd power is going to be negative. So your f of x would also be a negative infinity. So if x goes to minus infinity, f of x goes to minus infinity. When x goes to positive infinity, very, very large positive number, then f of x is a positive number raised to a big power, that's going to be positive as well. So this would be x goes to negative infinity, alpha of x goes to negative infinity. As x goes to positive infinity, alpha of x goes to positive infinity. That's what we have. Let's see what they do. Here's the first one, okay? Because the degree is odd, the leading coefficient is negative, the graph rises to the left and falls to the right. Okay, normally it would go in the opposite direction, but this negation sign here flips it over. Okay, so this will be as x goes to negative infinity, alpha of x goes to positive infinity. As x goes to positive infinity, alpha of x goes to negative infinity. Okay, does that make sense? Now, since we're here, I'm going to point something else out to you. Okay, this also sort of deals with, it's not the end behavior part, it's the in the middle part. Okay, a lot of times if your exponent is 3, you're going to have 3 minus 1, which is 2 what they call turning points. Okay, here is a turning point here, there's a turning point there. So if x equal, or the n equal 3, a lot of times that will mean 2 turning points here. So that's a very reasonable looking function. Okay, another couple things to point out to you. Your exponents here, 3 and 1, are both odd. That makes this an odd function. Whatever it's doing to the right, it does exactly the opposite to the left. Whatever it's doing to the left, exactly the opposite to the right. So that's an odd function. Just a little reminder of things we've already talked about in chapter 1. Okay? The second of those, x to the fourth minus 5x squared plus 4. All we're interested in now is the end behavior. End behavior only focus on that first term. When x is very large negative, raise a negative number to an even power, that's positive. Raise a positive number to an even power, that's positive. Okay, so these are both on the up and up. Okay, now what I was saying before, maximum exponent is 4. We expect usually to see 3 turning points. There's 1, there's 1, and there's 1. Okay, not always, but most of the time that's going to be the case. What's even more about this one? Even, even, even. So this is the even function, so it reflects across the y-axis. Okay, same thing happening on this side is happening on this side. So just a little bit of reminder there. Now, the third one, again, for some reason they gave us an odd function. Odd here, odd here. 5 and 1 are your exponents, odd functions. Okay, now this one you'll notice doesn't quite follow the other rule that I said. Okay, it has 5 as the exponent. It doesn't have 4 turning points. It only has 2 turning points. And that's because you're missing some terms in here. Okay, so don't sweat that, but it's just a general clue. At most it could have 4 turning points. It doesn't have to have 4 turning points. Odd function. When x is very large negative, that's going south, really, really big. When if x is very large positive, x to the fifth is going to be a very, very large positive because the leading coefficient is positive. Does that make sense? Okay. Now, it looked like somebody either came or left. It doesn't look like they came. Let me make sure by moving this up to the top. Yep. No new people here. But we still got, what was it, 15 students? Okay, I think that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah, we lost somebody. That's what was happening there. Hopefully they will be back. All right, any questions on example 2? A, B, or C? Okay, I can't get it to advance. Let me click on the slide, see if it'll advance. Okay. In example 2, note that the leading term test, I like to call it, tells you only whether the graph eventually rises or falls to the right or left. That's all it tells you. What happens in the long run? Very large negative, very large positive. End behavior. That's all you're dealing with. Other characteristics of the graph, such as the intercepts, the minimum or maximum points, must be determined by other tests. That's what I was suggesting to you. Some others, since we had the nice graphs there, I was pointing those out to you. So, we have just done example 2 on page 126. By the way, every example is followed by a checkpoint. Please do the checkpoints.
Mr. Fowler,
Yes.
it's not 30, just giving you a heads up.
Oh, okay. We got only 15 more minutes. Thank you. Okay. Alrighty. So let's look at the real zeros of polynomial function. These are what happens. The zeros of a polynomial function is where the y is equal to 0. So these are your x-intercepts. Okay, let's go back and just look at there. There's an x-intercept, there's an x-intercept, there's an x-intercept. Those are your zeros of the polynomial function, where the y, the f of x, is equal to 0 at -1, 0, and +1. Let's go back another one. This looks like it's probably at -2, -1, 1, and 0. Because these are even functions, they're sort of spaced out that way. Wait. -2, 1, 1, and 2. I don't know what I said, but it didn't sound right. This one, I think we already did that one. This one's at -2, 0, and 2. That's what we mean by the zeros of the function. Okay? This only shows 1, 0 there, 1, 0 there. Okay? That's what we mean by the zeros. This one only has 1, 0 here. This one only has 1, 0 there. Okay, that's what we mean by the zeros of a function. A 0 there and a 0 there. Now these that look real flat here, they're not really zeros. They're just very, very, very small positive numbers here, negative here, very small positive here. There's only 1, 0 right there where it crosses. Okay. So that's what we're talking about, real zeros of polynomial functions. It can be shown that for a polynomial function of degree n, and it looks like we lost somebody else too. I don't see anyone else coming in, and we lost one. Okay, it can be shown that a polynomial function of degree n, the following statement's true. The function f has at most n real zeros. Let's flip back again. If it'll flick back. Okay, this one, degree 5, it has at most 5 zeros, it only has 3. That's okay. It can have less, it can't have more. Okay, this one, degree 4, it has 1, 2, 3, 4 zeros. It maxed out at 0. You know it's not turning around and coming back again. It can't happen. Okay, it's already got its 4 zeros. This one, degree 3, 1, 2, 3 zeros. At most 3 zeros, it's got them all. Okay? We can't tell on these, so let's just go back here. Okay? Now, this is what I was saying before. The graph of f has at most n-1 turning points. A turning point is also a relative minimum or relative maximum that we talked about in the last chapter. Those are points where the graph changes from increasing to decreasing, decreasing to increasing. Those are your turning points. So finding the real zeros, finding the zeros of polynomial functions is one of the most important problems in algebra, and we'll be doing that. But let's go back and look. Like I said before, this has degree 5. It has most 4 turning points. This one only has 1, 2 turning points. That's fine. Okay. This one, degree 4, it had 3 turning points. 1, 2, 3. That's maxed out. All it can have. This one, degree 3, 2 turning points. 1, 2. Okay. Those are your turning points. Okay. there is a strong interplay between the graphical and algebraic approaches to this problem. Okay, when f is a polynomial function, a is a real number, that's that leading coefficient, okay, then the following statements are equivalent. Okay, I'm sorry. A is a different A now. Sorry about that. Now, these are all four ways of saying the same thing. X equal A is a zero of the function f. Okay, if that's true, then X equal A is a solution for that polynomial equation f of X equals 0. Why? Here's D coming back in. Glad he made it back. Because that's what it is. F of X is Y. Y is equal to 0. That's a 0 of the function. It's a solution of f of X equals 0. Okay? I don't know if somebody else is coming in or not. Let me see. I don't see anybody. Okay? Now, X minus A is a factor of the polynomial. If this f of X equals 0, if you factored that and got X equal A, then if you set that equal to 0, add A to both sides, a factor, X minus A is a factor, add A to both sides, you get X equal A. So this is a third way of expressing this. And then the fourth way, A0 is an x-intercept of the graph of f. So basically, this is saying, let me see if I can go backwards here. Okay, what was that? Okay, someone's microphone's on. Okay. X equal -1 is a 0 of the function. That means X minus 1 would be a factor of this function. X equals 0 would be a 0 of the function. X is a factor of the function. So you see all those four characteristics. -1, 0 is a x-intercept. 0, 0 is an x-intercept. 1, 0 is an x-intercept. Okay, all four of those characteristics of expressing that would be the equivalent. All four of those things are equivalent. So here's example 3. Let's see if we can get that done. Find all the real zeros of this polynomial function. Okay, got my pen turned over here. Guess what we're going to do? What's the F word? Factor. But I can't get my pen to write. The pen died. Okay, I hope that's not true because these pens are very expensive. So let me see. Okay. All right. First thing we would do was factor. Let's factor out a minus sign, a 2, and an x squared. Okay. Now, I wish I could write on here. That would be a minus 2x squared. What do you have left? An x squared here, a minus 1 there. Okay. So that would be a minus 2x squared times x squared minus 1. Okay, well, x squared minus 1 will factor again. That would be x plus 1 times x minus 1. Sorry, I can't write it. The pen just is not cooperating at all. I don't know why. This will work, but the pen won't work. Okay, now set those equal to 0 because that's why we factored. Set this equal to 0. Well, x equals 0 will obviously work for the minus 2x squared equals 0. That means x equals 0. The other was x plus 1 times x minus 1. Those are two other zeros. So we found the 3 zeros. Maximum you could have would be 4. It only has 3. Now, one of the reasons for that x equals 0 in that first one, that was minus 2x squared equals 0, x equals 0, or x equals 0. It has a double root at 0. Okay? Then it says determine the maximum possible number of turning points. Well, maximum degree here is 4. 4 minus 1 is 3. That should have a maximum of 3 turning points. Should have had a maximum of 4 zeros. We didn't. We only had 3 zeros. That's okay. The maximum was 4. 3 turning points, and indeed that will be the case. So let's see what we're going to do to find the real zeros. Set the f of x equal to 0. Just set that equals 0. Let me see if the pen will show up now. No, it won't. Okay. Then factor out what you can. Maximum factor here, minus 2x squared. Okay. When you factor out the minus 2x squared, that left you x squared minus 1 here, still equal to 0. Now let's set each of these. This factors as a minus 2 times x times x times x minus 1 times x plus 1. Set each of those equals 0. Negative 2 is never equal to 0. Throw that one out. X equals 0 is 2 zeros there. X equal 1 here, x equal minus 1 there. So the real zeros are x equals 0 from here, x equal 1 from there, x equal minus 1 from there. Okay? Factor it completely, set each of them equal to 0. You only have 3 here, even though you thought you could have had up to 4. This one's a double 0 at 0. Okay? Because the function is a 4th degree polynomial, the graph of f can have at most 3 turning points. And we see when we graph it, it will have 3 turning points. Okay? And here's why. In this case, the graph has 3 turning points. It crossed the 0 here at minus 1, 0. Then it had a double 0 at 0, 0. And then it had another 0 at 1, 0. Okay, so you had a turning point here, a turning point there, and a turning point there. Okay, so there are 3 zeros. Oh well, 3 zeros, 3 turning points. If that had not touched here and come down here, you would have had 4 zeros. Okay, but it came here, touched, and went back in the same direction. Here it crossed the x-axis. Here it touched the x-axis and went back in the same direction. Here it crossed again. That indicates this was a double 0 at x equals 0. We're going to talk about that later, but just to introduce it to you now. A single 0 here, a single 0 there. Double 0 there. Okay. In example 3, note that because the exponent is greater than 1, okay, then the factor negative 2x squared yields a repeated 0 at x equals 0. Like I said, you could say this was a minus 2 times x equals 0. Minus 2 is never equal to 0, but x equals 0, x equals 0. That's a repeated 0 at x equals 2. So anytime you have a factor, x minus a raised to the kth power, where k is anything greater than 1. Actually, it works when it's equal to 1 too, but you know, we'll leave it like that. That yields a repeated 0 at x equal a. And that's called multiplicity of k. You can have a multiplicity of 1, meaning there's only 1 0 there. Okay? It's not repeated, but it's a multiplicity of 1. Now, when that k is odd, okay, our k was even here. When that k is odd, the graph actually crosses the x-axis at x equals a. Well, we saw that. When k was 1, which is what this one is, that crosses, and k was 1 here, that crosses. When k was 2, even, it doesn't cross. It touches and turns back in the same direction. When k is even, the graph touches the x-axis, but does not cross the x-axis at x equals a. Touches there, kisses there, goes back in the same direction. If k was odd, it may hang around there for a while, but it will cross. Okay? To graph polynomial functions, use the fact that a polynomial function can change signs only at its zeros. It may not change at the 0, but that's the only place it can. Because, 2 reasons, polynomial functions are smooth and continuous. So between any two consecutive zeros, the polynomial must either be totally positive or totally negative. Between any two consecutive zeros, that's the case. So we're getting all these more characteristics of polynomial functions that you can see. That means when you put the real zeros on the polynomial function in order, they divide the real number line into intervals in which the function has no sign changes. Negative here, positive here, negative there, negative, whatever. Those resulting intervals are sometimes called test intervals, in which you can choose a representative x value in between those two zeros and determine whether the function is positive or negative. Whatever it is there, if those are consecutive zeros, it can't change signs again until it crosses. The graph either lies above the x-axis or below the x-axis. Okay, and we've just run out of time. Okay, now, yes, what's that? Okay, well, somebody else had a question too. Let me see where we are. I got carried away and didn't note where we were. We have done example 3. Okay, we'll be beginning next time on example 4, page 128. Homework exercises here would include, let me put my piece of paper in place here. On page 132, any of the odds 9 through 13, you should be able to do all those, but 9 through 13 will have answers in the back and at calcchat.com. 15 through 17, 15 or 17, both at CalcChat, 17's at CalcView. Any of the odds 19 to 27, they're all at CalcChat, 21's at CalcView. 29 or 31, both at CalcChat. I think you can do any of the odds 33 to 47. They should all be at CalcChat. 43's at CalcView. It says using technology, try to do 49 or 51. They should both be at CalcChat. We'll pick up the rest of those next time. Okay, now who was it? Was it Shay, or who had the question at the beginning? Okay, Shay, what was your question? Oh, okay. Okay. Well, I can't have two of you having personal questions at the same time. Do you want to email it to me, or what would work? Okay. All right. And who was the other one? Terrell? Terrell? I'm sorry, Terrell. Okay. You want me to go on and stop the sharing? Okay, what's the question? What's that again? Well, I can. If everybody leaves, I can't kick them out. Okay. But if I end the meeting for everybody, I'll lose it for you too. So do all the rest of you want to check out? People are leaving now.
If there's nothing else, Mr. Fowler, I can go on and leave. This is Janae.
Janae, okay. Oh yeah, that's all I've got for today. Right. Thank you. You do, well, we'll see you on Thursday. All right, good deal.
Yeah, just give me your, yeah, I got you.
Okay. All right. Okay, was that taken care of, or do you still need me on? Oh, you still need that. Okay. Okay, waiting for everybody else to leave. We only got about 1, 2, 3, 4, 5, 6 more. Okay, down to 1, 2, 3, 4 left. Yeah.
When is a day that you're free? We can go over the test, like a couple questions that I
Okay.
need the answers to.
Okay.
Or we can on Zoom meet or anything.
Okay. Okay. When did you want to do that?
Oh, whenever you're free.
Okay. Well, I'm in class just about continuously today until 7:45 this evening. I mean, this is my full day. I've got four classes. One of them's a mini term with a lab. So
Okay, so
between but tomorrow, okay, today from 1 to 3 I've got some free time, and tomorrow from 8 to 10 and 4 to 6 I got free time, so whatever works best for you.
I can do tomorrow 4 to 6.
4 to 6, okay. You going to email me or call or what?
I call you.
Okay, alrighty. Okay, so that'll be tomorrow 4 to 6. Now sometimes I have advisees then. I don't know that I'll have any, but if not, that's only between 5 and 6. So if you can do it between 4 and 5, that might be better. Okay. All right. Down to 3 people still in here. Okay. Okay. Bye-bye. Okay, only got 2 left, Jemiah and Rosa. Okay, we lost Jemiah. How about Rosa? You still there? Okay.
Yeah, I'm there.
I know Terrell is still here, but Rosa's still online too. So
Okay, it's not that part of my
okay,
speech, actually. I just want to hope everybody knows what I need to say.
okay. Well, what is it? Because I got another class starting in 9 minutes.
Okay, so I went on calchat.com
Right,
and I was talking to an agent, who works at my so when I was looking at some of my previous work, the assignments that we were doing, they were telling me that they did not know what was like what was what. So when I started scrolling, I seen where it had like this, like chapter 1 through 16, different sections with no page number. So I think I emailed you yesterday or day before that, one of them, and I asked you, I was not quite sure on which chapter, but you said today chapter two. But if I go back to chapter one, just hypothetically, just say 1.2, well, it's on another side, it says section one, section two, section three, and I don't understand because I don't have the hard book. I'm looking at Calvin. So I think I'm just confused about that.
okay. I'm
So what I'm asking you is,
yeah.
I don't understand how to get the problems that we are going over. So it has different sections, I mean chapters, one, and I remember like 1.2 was something that we did in chapter one, but it doesn't say 1.2. It says section one, section two, and section three. So
Right,
it's confusing to me because I didn't know. I didn't want to just start doing problems and they wasn't what we were doing. You know what I'm saying?
right. Okay. In chapter 1, there are sections 1 through 9. I know there may not be. We didn't do 1 through 3. We started with 1.4. So in chapter 1, we did sections 4, 5, 6, 7, 8, 9. In chapter 2,
Wait a minute. I'm trying to hurry up. I want for your class. So you said chapter one.
we did sections we in chapter 1 we did sections 4, 5 and 6, 7, 8 and 9. In chapter 2, we did sections 1 and 2, that's what we're on now, and we will do 3, 4, 5 and 6. We will not do 2.7.
Okay, cool. So chapter one,
4, 4 through 9,
okay.
and chapter 2, 1 through 6.
Right. Okay. So you just answered my question. I was like so off and confused yesterday. But I got you. So that's pretty much it.
Okay.
And I emailed you my test too.
Okay. All right. I was yesterday we were just getting back into town, and I had I was just in pretty bad shape, cold wise, nasal, everything was messed up yesterday. So I'm a little bit better today. So I haven't gotten to any emails over the weekend. I was out of whatever you call it, ether space. I mean, you could hardly get emails where I was. I was out in the country in Georgia. So anyway, I I feel like I'm getting less anemic every day. I feel a little bit better. I don't hear the heart beating as much. I don't feel as stressed. So I think it's getting better every day. But it's I have another appointment in mid this month. About the 17th, 18th. They're going to check again. So we'll see how it goes. Uh huh. I'm sorry. Okay. I guess that could be. Okay. Well, good. Thanks much. And we'll see you then on Tuesday, right? All right. Okay. Take care then. In. Okay. Bye bye.